We are starting our new unit on the chemistry of life, and today is going to be kind of a deep dive into really surface level chemistry. So if you're a little intimidated by chemistry, don't be. This is going to be just kind of like the common sense things that everyone needs to know. So let's get started. We're going to start off with some discussion on basic chemistry. So this is things like identifying the components that make up a matter and the structure of atoms, what's an element and a molecule and an isotope, and then the different types of bonds that can form. Here's a bunch of the key terms. And just like with the ecology unit, this has to start with the idea of life is organized. This is one of our properties of living things. We talked about how life was organized from the organism level and up, and now we're going to look at how it's organized on the bottom side. So all life's organization begins with the smallest unit of matter, and that is the atom. The atom is the basic thing that makes everything up in the universe. Atoms come together to form molecules. Molecules can come together to form organelles, and the organelles come together to make cells. Groups of cells that behave similar and have similar structures are called tissues. And then a bunch of similar tissues working together with other similar tissues create organs. I think I mentioned this in class before, but your heart has cardiac muscle tissue, connective tissue, all of that works together, the liquid tissue we call blood, to create your heart. Then organs with all of their accessory components make up organ systems, and the organ systems all come together to create one living organism. So chemistry involves an elaborate deep dive into both matter and energy. However, this time around, we're really just going to focus on this matter aspect. The energy we're going to get into when we talk about photosynthesis and cellular respiration. So matter is anything that has mass and volume, and as you've probably been learning since elementary school, there's the 4 states: solid, liquid, gas, and plasma, and that all matter is ultimately made up of these structures called atoms. So atoms are the smallest particles that keep all of their original characteristics. Anything smaller than that, and they don't have the same characteristics anymore. You can have many atoms of the same element together, and they will all have the same characteristics as each other. So the atom structure is divided into 2 main parts. There's the nucleus. This is the dense central part of the atom right here, and that is containing most of the atom's mass. Some of the mass is found outside of it in the electrons. But inside the nucleus we have protons, P for positive, P for proton. These are the positively charged particles that are found in that nucleus. These are important because the number of protons in the nucleus give the atom its identity. So an atom with 1 proton is hydrogen. An atom with 2 protons is helium. It actually makes up how we identify them. The other part of the nucleus are the neutrons, and neutrons have no charge. They are going to be neutral particles. Surrounding the nucleus is the electron cloud. This is where all of our negatively charged particles, the little electrons, kind of zoom around the nucleus. They are constantly moving, and it's these electrons that allow the atom to interact with other atoms. So elements are the different types of atoms that each have their own unique characteristics. So we can put a bunch of atoms with 1 proton together, and we call that hydrogen. Hydrogen can be just one of those atoms, or it can be 1,000 of them together. So they are pure substances that can only be broken down into identical atoms that all behave the same way. They all have the same number of protons. So in this case, if you have 6 protons in your nucleus, you are carbon, 1, you are hydrogen, 8 oxygen, etc. Now, isotopes are atoms with the same number of protons, because we're talking about the same element here. However, their nuclei can contain two different numbers of neutrons. Remember, these are neutral, so they don't add or change the charge at all if we add or subtract them. So the protons and electrons, the positive and negative, should be balanced the whole time, but the neutrons, we can kind of mess around with their numbers a little bit. Now, it doesn't change the identity of the atom. We're still going to be dealing with a hydrogen or a carbon. However, that carbon may have slightly different properties than other carbons that have different numbers of neutrons. So these isotopes have identical chemical properties but different physical properties. Their melting point might be slightly different between the two versions of carbon. Their density might be different, things like that. So here we see an example of a protium atom right here, a protium isotope. That is just hydrogen with no neutron. Then we have deuterium, which is hydrogen with its one proton. We always have the one proton because that's the identity of hydrogen. But this one has one neutron. Now, tritium has two neutrons in there. So these are all different isotopes of hydrogen. Now, the electrons orbit the nucleus in what we call shells or orbitals. They don't just wander aimlessly around. They have a most likely path that they travel. And within these shells, they exist in specific quantum states, so basically in specific areas, and we just give it the term shell. You may have heard them called energy levels in the past. And the first shell, the first one, if this is the nucleus right here, the first shell around that can hold 2 electrons because that's how much energy is available in that particular area around the nucleus. The next level can hold a maximum of 8 electrons, and so on and so forth from there. You can get more and more energy, or you get more and more electrons as you get to higher energy levels because there's more energy available there. So as they orbit, they have an outer shell depending on how many electrons they have. And the number of electrons should, in theory, be equal to the number of protons so that your overall atom is neutrally charged. But that very outer shell, the very outer energy level, we like to call it the valence shell. And this shell, this energy level, is a little picky. It constantly wants to be energetically stable. It wants to be what we call full. So either the atom will have to gain electrons until it hits 2, or lose electrons until it hits 2 or 8 electrons in that outer valence shell. That's just the most stable configuration for the element. Now, the problem is, depending on what element you have, you may not have enough electrons to fill that full valence shell. As a result, these different atoms are going to then interact with other atoms so they can fill that valence shell and be stable by forming chemical bonds with each other. So if you want to deep dive on electron shells and orbitals, because we get into some crazy physics there that we do not have to understand for this class, I will attach a video to the PDF that you can watch. So the problem with the electrons, as I said, is they like to have full valence shells. So atoms will either gain or lose electrons in an attempt to get that full number of either 2 or 8. As a result, we go through chemical reactions, or the atoms go through chemical reactions. So 2 or more of the same element or 2 or more of different kinds of elements will interact with each other and recombine in new configurations. So the materials that go into a reaction, right here and right here, those are your reactants, the ones that are going to react with each other. The things that are made at the end are the products, the things that are made. So during these chemical reactions, bonds are formed between the different atoms. Sometimes that's because they share the electrons together. Sometimes it's because one atom will completely lose electrons and give them up to the other atom, and then they'll have a positive and negative attractive force with each other. But basically, what happens is that interaction between the atoms is called a bond. Now, molecules are formed when two or more of the same element bond together and share or distribute electrons with each other. That's going to be something like oxygen gas or nitrogen gas. It's two of the same element bonded together. Compounds are formed when two or more different elements bond together. Something like water, or something like hydrogen peroxide or methane. Those are all multiple different atoms of different elements bonding together. Now there's two major types of bonds. The covalent bond, which is where there's a sharing of those valence electrons, those outer electrons between the atoms. So one atom doesn't completely take them or give them up. They say, okay, we both need these electrons, let's share them equally with each other. This is often things like our carbohydrates, things like carbon dioxide, methane, fats, DNA. These are all made of covalent bonds. Ionic bonds, on the other hand, are those that form between what we call ions or charged atoms. You get a charged atom when you either give up or steal electrons from another atom. So a cation is one that loses electrons. If you lose your negative charge, you are no longer having equal positive charges from the protons and negative charges from your electrons. They're no longer equal. So if your number of electrons goes down, you're going to have more of a positive charge to your atom. So cations become positively charged. Anions, what ends up happening is they gain electrons. So the number of your, trying to erase this here for you. The number of your electrons actually increases. Now you have an imbalance in the other way. You're going to have an increase in the negative charge compared to the positive. So your anions are more negative. As a result, positive and negative forces often attract each other, so these ions will actually be attracted and form an ionic bond with each other. So here's an example of that ionic bond. This metal transfers its one electron to this nonmetal, and this now is a positive cation, and the nonmetal is a negative anion, and that creates an attractive force between the two, and they bond together. In a covalent bond, neither of them gives up their electron, instead they share them together. But there is a third bond that tends to dominate a lot of interactions between molecules and compounds. This is not a true bond, but we call it one, and that is the hydrogen bond. So these are merely attractive forces between slightly negative and slightly positive areas on different molecules or different compounds. So we're not talking about atoms bonding with each other. We're talking about molecules and compounds being attracted to one another. So in this case, we call these molecules that do these attractive forces and form these hydrogen bonds polar molecules. When you think about the word polar, you think of the North Pole and the South Pole, opposite ends of something. That's kind of the same idea here. What's happening is there's going to be an unequal sharing of electrons in a covalent bond. One of the atoms in a covalent bond is going to hog those electrons a little bit more than the other atom. So they are going to hold on to those electrons a little more. They're going to become slightly more negative, while the ones that are holding on to the electrons for less time are becoming slightly more positive. And as a result, those slight positive and slight negative areas want to attract to other positive and negative areas that they encounter in the environment. And once again, I'm anthropomorphizing it a little bit just to make it stick in our heads a little bit easier. These chemicals don't want to do things. These positive and negative forces just are attracted to each other. That just happens. So in this case, the slightly positive area of one polar molecule is attracted to the slightly negative area or fully negative area of some other molecule, and vice versa. Now, overall, these polar molecules are neutral. They don't have an actual charge. It's just that one area is a little more negative and the other area is a little more positive, but overall the molecule is not charged. So it's not like, oh, here's this molecule, it's positive or it's negative. It's still neutral. It just has positives and negatives starting to emerge within the molecule itself. So we're going to discuss this idea of polarity in a little bit more depth now when we discuss water, because water is the main polar molecule, and water is so crucial to all of life. And because of the way water behaves due to its polarity, it allows life to exist. So let's dive in. Here are some of your objectives, things that you should be able to do by the end of this, and some of your key terms. So looking at our water properties, all of these properties exist and allow life to occur because water is polar and because it can form hydrogen bonds as a result. So we're going to talk about all of these different properties in a second. So first, let's look at water's structure to understand how it's polar. So we have water is H2O. What that means is that there are two hydrogens and one, we always assume that there's an implied 1 at the end here if we don't actually write a number, so 1 oxygen. So how they come together is you have the oxygen in the middle and the two hydrogens are going to bond in this kind of upside down or I guess right side up V shape depending on how you're looking at it. So it makes this angle in a arrowhead shape. Now oxygen has extra electrons and as a result that makes it what we call electronegative. It wants to grab onto electrons more than it wants to give them up. In order to fill its valence, it needs 2 electrons. So it wants to take those 2 electrons whenever possible. However, it is sharing the electron that the hydrogen has. Hydrogens normally only have 1 electron. So that 1 electron that they are sharing, it gets kind of pulled towards the oxygen more often than it's given to the hydrogen. The oxygen is kind of like the hog of the toy. It's the kid that doesn't know how to share properly. So it shares, but it plays with the toy 70% of the time and only gives it 30% of the time to the other kid. So as a result, the oxygen is going to have a partially negative charge. And as a result of that, the hydrogens are going to have partially positive charges. That is what is going to create that polar characteristic of this water. It is now slightly negative on one side, slightly positive on the other. So how does that lead to the formation of a hydrogen bond? Well, that slightly negative oxygen can form an attractive force with the slightly positive hydrogen on a different water molecule, just like you see in this picture here. So water readily forms hydrogen bonds with itself. All of the molecules as they're interacting with each other are constantly forming and reforming and breaking these hydrogen bonds. So cohesion and adhesion are 2 of the first properties of water that come about because of these hydrogen bonds and this polarity of water. These are just properties that cause water to form bonds, hydrogen bonds, with itself and with other materials. Cohesion is particularly when water molecules hydrogen bond to other water molecules. It's hydrogen bonding to itself, just like that last image that I showed you. And as a result, we can see new properties, new behaviors of water start to arise because of this cohesion. And one of those is surface tension. So if you've ever seen, like in this image down here, bugs or tiny pieces of dust or anything like that float on top of water and not break the surface of the water, you are seeing surface tension. What you're seeing is that attractive force of all of the hydrogen molecule or the hydrogen bonds forming between the water molecules at the surface is so strong that these creatures or this dust cannot break through that water. And as a result, they get to walk on top of it or lay on top of it. Another thing is adhesion. This is when water molecules hydrogen bond to other molecules that have positive or negative charges on them. So we can see that in this image on the right with the water droplets forming on the spider web. They are being attracted to positive and negative forces on the spider web itself, causing it to stick. Just like how if you step out of the shower, you're not magically just all the water falls off of you and you're dry. The water clings to the positive and negative charges on your skin as well. Another cool thing about cohesion is that as a result of that surface tension, water tends to form droplets. That's only because it's trying to form all these hydrogen bonds with everything around it, and that forces it to make this really cool circular shape. So here is the example of cohesion, water hydrogen bonding to water because of the slightly negative oxygen wanting to be attracted to the slightly positive hydrogen of a different water molecule. And adhesion is when it sticks to some other kind of polar or charged molecule. So in this case, we have the nitrogen that's going to be the electron hog, so it is slightly negative, and the hydrogens here are slightly positive, just like the hydrogen is slightly positive on this water. So that way the hydrogen and the nitrogen are slightly attracted to each other and they form that hydrogen bond. That is adhesion. Think of it like they're co-workers, it's the water working together. Adhesion, think of Band-Aids. We used to call them adhesive bandages. They are something else that is sticking to your skin. It's not skin sticking to skin, it's the Band-Aid sticking to you. The next property of water that's really interesting is capillary action, and we have to understand cohesion and adhesion in order to understand this emergent property of capillary action. So this allows water to somewhat defy gravity using only the power of cohesion and adhesion. So when we think about these gigantic trees, and we're lucky enough to live in California with some of the tallest trees in the world, the redwoods, how in the heck does the water get from in the soil all the way up to the leaf at the very top of the tree? And how does it get into the root hairs? They're so tiny. Well, those root hairs are actually part of the reason why the water can get into the plant. The root hairs are insanely tiny tubes, and capillary action is this phenomenon where water is drawn up a small tube without any suction being applied. So you don't have to suck up the water, it is just naturally going to start moving up this tiny tube. Why, you might ask? Well, adhesion causes the water to adhere or stick to the insides of this tube. The cohesion keeps the water touching all the other water molecules around it. So these strong properties of adhesion and cohesion grip the inside of the tube and actually start pulling the water up against gravity. Basically what it's saying is the forces of adhesion and cohesion together, these hydrogen bonds, are slightly more powerful than the force of gravity in drawing that water up. Now, eventually, there is going to be a maximum of how high the water can get given the diameter of the tube, because then at some point, the force of gravity is not going to be able to overcome that upward force being created by the hydrogen bonding, cohesion, and adhesion forces. So eventually, it will stop at some point. But we can see here in this graphic that the adhesion is drawing the water up on the side, and the cohesion is keeping all the water molecules together in the middle. We can see here that the smallest capillary tubes allow the water to be drawn up the highest. Larger tubes, the water can only be drawn up a little bit compared to the smaller one. So if you really are interested in this and you want to deep dive about the rest of the story, because capillary action is actually only the first part of how water gets into these gigantic trees. How does it then keep going upward? Because these tubes don't necessarily get all that smaller. They get bigger as you get towards the center of the tree. So what force is continually drawing that water up to the top of the plant? I will link in, once again, the PDF, a really cool video that explains the rest of the process. Now, if you've ever spent a day in the San Fernando Valley and then driven over to LA, you might think, what the heck? I only crossed one mountain range. Why is it 20 degrees cooler? Why am I baking in the valley, but it's a beautiful day in Santa Monica, for example? Well, it's actually all because of water. Water has what we call a high heat capacity, and it is what allows coastal cities to remain cool compared to more inland cities. Specific heat capacity is just defined as the amount of energy required to raise the temperature of a material, in this case water we're talking about, by 1 degree Celsius. So how much energy does the water have to absorb or take in before the temperature of the water goes up by 1 degree? And you might think that's not the same for every structure on the planet. No, it's not. Metals tend to only need to absorb a small amount of energy before their temperature goes up. That's why if you are cooking soup and you accidentally leave the spoon in a little too long and you go to grab the spoon, it is insanely hot and you burn yourself because they change temperature quickly. They have relatively low heat capacities. Whereas water is way down here on the bottom of this chart. Water absorbs tons of energy before it is able to change its temperature. And why might that be? Well, it's all because of that hydrogen bonding, that cohesion that's occurring in the water. The water molecules have all these attractive forces between them, and the heat has to break those attractive forces to separate the molecules from each other and allow them to move more freely, which then increases their temperature. So water can absorb a lot of heat before it actually goes up in temperature. And also the opposite. It takes a while of water radiating or giving off heat before it cools down. That's why, you can leave your tea sitting out for a while and it's not going to immediately get cold. So what this does is if you have a large body of water, like an ocean or a lake, that water is going to absorb a lot of the heat coming near the city, and it's going to keep the climate actually relatively cool compared to other areas nearby that are a little bit further from the body of water. Another very fascinating aspect about water is that it exists in all 3 states of matter at the same time on our planet. You can go to some places and find water in its liquid form, you can find it in its solid form, and its gaseous state all at the same time. But when we really think about most materials, when they are in their solid form, they have a very high density, especially compared to their liquid form. So if you take some metal or something, and you take a solid ball of that metal and you place it in a liquid of that metal, the solid ball of that metal will sink to the bottom because it's more dense than the liquid form of that same metal. Water is not the same. In water, actually, its solid state, its frozen state, ice, floats on top of its liquid, meaning its liquid is more dense than its solid. So why is that exactly? Hydrogen bonding. It all keeps coming back to this polarity and hydrogen bonding. So liquid water has a little bit more heat in it, a little bit more energy, so these molecules are not forming as many hydrogen bonds. They're more zooming around a lot more frequently. When we start to remove that energy, they form these very intricate hydrogen bonding patterns. They start to form these lattice-shaped structures, and they form these really beautiful honeycomb structures. But they actually have a lot of space in between these molecules. As it freezes, it expands, trapping, basically you can think of it as trapping more air inside, but really it's just that there's more space in between all of these different water molecules. So as a result, it's less dense and it doesn't sink to the bottom of the body of water it's on. This is actually incredibly important for life because if solid water, if ice, sunk to the bottom of liquid water, then it would cause all of the water on the bottom of a body of water like a lake or an ocean to start to get colder and colder and freeze over, which would then freeze over the layer on top and the layer on top, and eventually you would have your oceans completely frozen solid. Whereas this way, the ice freezes and stays up at the top. And what it does is it actually prevents an interaction from the air and the water, and it allows the water to stay warmer than it otherwise would be. It would get colder and colder if it kept being exposed to the air, but instead the ice is insulating it, allowing life to continue to live despite the freezing cold temperatures in the atmosphere. So just kind of fascinating to think about. Another property is that water is known as the universal solvent. What we mean by that is that it can dissolve almost all polar substances. So how does water tend to dissolve or kind of integrate these polar substances like sugar and salt? Well, the key is it forms things called hydration spheres because of its hydrogen bonding. It all keeps coming back to that hydrogen bond. When we look at something like table salt, which is NaCl, this is an ionic compound. The sodium is positive and the chlorine is the negative ion. But these are actually charged ions. So the slightly positive and the slightly negative areas of water are going to be attracted to these slightly positive and slightly negative charges of the table salt. And what they do is they form these things called hydration spheres around the ions. So the water will actually start to be attracted to the positive and negative areas, and it will start to pull them away with their hydrogen bonds from each other. So the sodium and the chlorine will be separated from each other, and water will form these rings around each individual ion. So if the sodium is the positive ion, then it will be surrounded by the more negative aspects of the oxygen. If we're looking at the negative ion, the chlorine, you will see that it is surrounded by the more positive hydrogens rather than the negative oxygens. So because it can do this, we call water the solvent, the thing that does the dissolving, and we call the compound that is being dissolved the solute. Together they form something called a solution. So when water is the solvent, we call it an aqueous or aqueous solution. I've heard it pronounced both ways. And that just means a solution where water is the solvent. Now, oils, waxes, fats, these are what we call non-polar. They share their electrons equally between all atoms. There is no slightly positive or slightly negative area. They're all neutral all the way around. Because of that, water cannot degrade these molecules. Just like if you've ever seen vinegar and oil together, they don't mix. They form completely separate layers because the water has nothing to act on. It has no positive or negative areas to be attracted to. However, there are nonpolar solvents that can dissolve these. That's a topic for another time. Now, compounds that hydrogen bond to water are called hydrophilic. Hydro meaning water, and philic coming from the word love. So this is something that loves water. Whereas compounds that are nonpolar are called hydrophobic, and that word phobic comes, it kind of relates to that word phobia. This is fearing water. So hydrophilic compounds love water and are attracted to it, and they can form hydrogen bonds with that water. Anything that is nonpolar cannot form a hydrogen bond, so no hydrogen bonds, and we call it hydrophobic. And there's a scale to how hydrophilic or how hydrophobic certain substances are. We have super hydrophilic substances where they very readily form hydrogen bonds with the water. And then we have super hydrophobic compounds that almost repel water. So when you ever are thinking about, I have to design something that has to be surrounded by water and be unaffected by that water, you might want to consider using one of these super hydrophobic materials to build your prototype or your design or whatever you're doing as an engineer, to try to limit how much that water is going to be interacting with the surface of your structure. So we consider those super hydrophobic things to be almost water repellent. The last topic that we're going to discuss in this video is pH and buffers. So be able to do all of these different objectives. Here are your key terms. Now, water, because of its ability to hydrogen bond, will often shift between different chemical forms. So basically, as it's hydrogen bonding, sometimes that attractive force of that hydrogen bond gets a little too strong, and that hydrogen pops off, and you end up with something called a hydronium ion, where you now have 3 hydrogens per 1 oxygen, and you're left over with a hydroxide ion of 1 oxygen, 1 hydrogen. As a result, these two structures have a real charge to them. They are no longer neutral. Hydronium is positive and hydroxide is negative. So when we talk about this unequal sharing of electrons with polarity, we sometimes create these new structures entirely. Now, in pure water, these positive and negative charges of hydronium and hydroxide balance each other out. So pure water has a neutral pH, a pH of 7. A solution that is more acidic, it means it has more of these hydronium ions. And as a result, it's going to become more and more positive. A solution that is more basic or alkaline has more of those hydroxide ions. So as a result, it's going to become more and more negative. So pH is simply a measure of how many hydrogen ions are in a solution. So when we talk about it, it's thought to stand for the potential or power of hydrogen. That's what the pH is there. And it's measured on a logarithmic scale. That means every tick does not equal the tick before it. So if you go up in number by 1, you're actually going up by 10-fold. So the amount of hydrogen ions is increasing 10 times each number you add. So from a pH of below 7 to 0, so from 0 to 6.9, you're going to have something that has a very high concentration of H+, basically those hydronium ions. Those often will dissociate into or break apart into hydrogen ions and water. So that's why we say it has a high concentration of hydrogen ions, or H+. Now, something that is from 7.1 to 14, we're going to call that basic or alkaline because it has a low concentration of hydrogen ions. It's going to have a lot more of those hydroxide ions. So 0 to 6.9 is going to be an acid. Let me write that over here. And then anything above 7, from 7.1 to 14 is going to be your base or alkaline. And remember, right at 7 is considered neutral. That's your pure water. They're perfectly in balance. Now, there are structures that, chemicals that resist changes to pH, and we call these buffers. So sometimes when you add a small amount of acid or a small amount of base, it can cause massive changes in the pH. And sometimes you don't want that to happen, especially if you're doing scientific experiments. You want the pH to stay as level as possible so you can test some other variable. So we will use these different buffers. There's a bunch of them listed here that resist changes to the pH. They're basically chemicals that minimize the hydrogen ion concentration so we don't have a drastic shift one way or the other. And usually these are acid-base pairs chemicals. So the acid can take up the hydroxide that's extra, the base can take up the extra hydrogen ions in the solution. And different chemicals have different buffering ranges. So if you're doing an experiment, you'll have to pick the right one. I used tris hydrochloride a lot, and its range is from a little less than 7 to about 9. And I was testing a bunch of pHs in about the 8 to 9 range. I also used MES, and I wanted to test the growth of my bacteria right at that pH range. So there you can see how different buffers are important to what you want to do. And that is it for this basic chemistry lesson.